Good morning, everyone. So I'm Zhou from FIAS now in Frankfurt. So today I first want to thank Geiger invited me to present some our recent neural network study here, and I want to show some preliminary results on neural network study on the lattice 1+1 dimensional scalar field theory analysis. And this work is in collaborated with Goethe-Universität, Longgang Pang, who is now working in Berkeley, and Horst Stöcker. And for this study, the lattice configuration is generated by Goethe-Universität. Okay, so we already heard the previous talks that we know nowadays the deep learning has been much more popular. It's everywhere in our daily life, from beating the human beings champions in the game of Go to do a very good job at the image classification and the object recognition task, and to even transfer and extracting the artistic style to other artistic work. So we may be wondering why the deep learning has such a powerful abilities and what it's really doing in a much more intuitive sense. It's actually simple. It's just doing a function approximator. So if we want to perform a neural network, there's only 3 steps. So first, we design some neural network structure. This can define a family of the functionals. And hopefully, we want to know that within this functional family, there would exist one specific function to well approximate our task. And the second step is we can evaluate using the data, the performance of the network structure, which function performs good or not good. And the third step is using the backpropagation. We select the right functions to do the job. And the only concern is in the step 1 that we may be wondering if there exists a good function to approximate the task. So there is a very restricted mathematical proof. It's called the universality theorem. It's saying that any neural network with at least one hidden layers can approximate rather well any smooth functions to any accuracy as you want. So we are ensured that once we defined a neural network structure with more than 2 hidden layers, it can mimic our task. We just need a very good optimization technique to select the pertinent functions. Okay, so among different neural network structures, the convolutional neural network is really better, good at the image classification problems. So it has been proven to be very good at the pattern recognition to process our image, some structured data. For example, for this handwritten digit recognition, the convolutional neural network can extract the abstract meaning of this image. We need to note that to the network or to the computer, the handwritten digits is only a matrix. It's a matrix of the pixel intensities. And there are lots of fluctuations being associated with each image. And the convolutional performance, the convolutional procedure can try to get rid of all these fluctuations and only converge to the much more higher level representations of this image. So this somehow is very similar to the renormalization group procedure in physics. And before diving into the specific content of this study in this talk, I want to mention a little bit of our group at FIAS. It's called Deepthinkers. It's began from last year. And we are mainly focusing on the artificial intelligence techniques application in disciplinary scientific research and also beyond. Some industrial collaboration is also performing. So I listed some typical projects we are doing. So first is applying the deep learning technology in statistical physics and try to analyze the lattice quantum field theory configurations. And we're also performing the decoding the medium properties from the heavy ion collisions using the deep learning approach. Basically, we feed in the detector's final output in a heavy ion collisions into neural network and let it tell us the information about the medium it created. And we're also doing such a project that to simulate the hydrodynamic using the deep learning, try to speed up the simulations. And with the outside company, we are working on such a project called the Smart Valve that basically we want to analyze the valve working status and also the flow status inside the valve by just hearing. From the recorded acoustic signal, we successfully get information about the leakage information, about the flow status. Is it a cavitation or it's a turbulent, or it's in which stage approaching the cavitation? Do we need to tune the valve to avoid some damage? And also the flow speed inside by just hear the valve. So today in this talk, I want to show some results on the first project about the neural network study on the lattice configuration, and we only focusing on a very simple system. It's the lambda phi 4 theory, and we are only talking about the 1+1 dimensional case. And for this system, if you are a physicist, you would know that the Euclidean action for this system would be complex when we go to finite chemical potential. Because the chemical potential would appear in the Boltzmann factor, the partition function will be a very oscillatory integrand under the path integral. And there we cannot get a real valued probability to perform the normal metropolis Monte Carlo approach. And for this system, there's an approach called the dualization approach. It's also called world line formalism to tackle this complex action problem. It's basically try to expand the Boltzmann factor inside your formula on the neighborhood lattice sites. And we can represent our system, our phi 4 field, using the expansion index. And for 1+1 dimensional lambda phi 4 system, finally, we can get the dualization representation for the field is only 4 integer valued variables because it's 1+1 dimensional. So for the index, we only have the t component and x component. And the four variables are we denote as kt, kx, lt, lx. And it's all integer valued. And for kt and ks, it can be positive, negative, and for lt, lx, it's only positive. This information is not so important for non-physicists here. So I just want to show you one typical configuration. So it can be regarded as such 4 images. And for the system information, the mass we are chosen to be 0.1, and the interaction is chosen to be lambda equals 1.0. And we also tried different interaction values here. And the lattice size is chosen to be 200 by 10 for the time component and the spatial component. And for this dualization approach, we will get a very restrict constraint on the configurations that's called the vanishing divergence. It's basically a flux conservation of our field. And the formula is here. This is the only formula I want to show here, because this will constrain the configuration to be physical. And once we want to generate some new configurations, we also need to check this constraint to see if the configuration you generated is a physical one or not. So that means the spatial component of the key values, it must satisfy such a formula here. Okay, and for using this parameter setup, and after doing the dualization approach, we can evaluate the physical observables for the system, and this is the results for a ground canonical ensemble. Here is the chemical potential, and the green points are the particle number density. So we see here there is a transition point. It's not exactly a phase transition, but we call it a transition point here. That's because for 1+1 dimensional system, physically there would be no transition in the Landau's sense, but still we can observe such a non-zero condensation phenomena happening. And in this region, the particle number density is irrelevant, it's independent with the chemical potential. This is called the silver blades phenomena. For physicists, you may know this term. And the red points are the squared field value, the phi square. And we say it's associated, there's a strong correlation with the number particle densities. And for this setup, we get the transition point is in this chemical potential value, and this is 0.94. And basically, this value is just the physical mass of the system when we're using this parameter setups. So this is the background of the system we are studying. Now, we also generated some configurations for a different interaction, lambda equals 0.5. And for the generation of the configuration, we used the Monte Carlo approach. And this is to prepare us some training examples when we want to do a neural network study. So what we are targeting at using the neural network. So we tried search for different things, try to explore the possibilities that neural network can help us in physics analysis. And the first one is a classification task. We try to differentiate the configurations with different interactions. That basically means we can assign different lambda values for the configurations. We want to say, by looking at only the specific configuration, can the network identify the lambda values from the configurations, solely from the configuration? And the second task we tried is if the network can help detecting the phase transition information based solely on the configuration information. And the third task we tried is, can the network learn the physical observable from the configurations? We know, physically we know, given a configuration, if you know the formula, you can calculate the physical observables. So we want to know, can the network learn this physical dynamic observables from some training set? And is it possible to generalize to some different domain of your configurations, like and different chemical potential and different mass or interaction case? And the fourth case we studied is the neural network can learn the configurations meaning and can generate some new configurations. If this can be true, then this can help us avoid the Monte Carlo approach. You don't need to perform the Markov chain process in generating the configurations. And maybe this can also generalize to other physical parameter case, like approaching the critical point, because we know physically when we approach the critical point, if we just use the normal Monte Carlo approach, the metropolis method, that would be the critical slowdown, because there the correlation length would be infinite, and if you want to generate an equilibrium state, we need to wait until your system be equilibrium. And the equilibration time is proportional to the correlation length. So at that point, the conventional approach is really inefficient. So if this can be true, this might give us some insight how to avoid the normal Monte Carlo approach to generate new configurations. So this is the 4 basic targets we want to explore. And in this talk, I show you some preliminary results on these 4 tasks. So first, let's look at our neural network structure. And as we said, the convolutional neural network is really powerful at the image processing and the image classification task, because we already seen that the lattice configuration can be regarded as 4 images respect to the 4 different integer valued variables, the k and l's. So we use convolutional neural network, and the structure is designed to be in this way. So we have 2 convolutional layers, and each followed with average pooling layers. And the input is the lattice configurations. We put the 4 images, we stack the 4 images in a depth direction. That means we have 4 channels for our input, the KT, KX, LT, LX. And in the convolutional layers, we applied also the L2 renormalization techniques. And during the convolution, between the convolutional layer and the pooling layers, we also put the dropout layer and also the batch normalization layer. This can help us to avoid overfitting. And for the weight initialization, we use the Gaussian distribution to normalize them and applied the L2 regularization to help avoiding the overfitting. Because we are targeting at a classification problem, so the loss function is chosen to be the cross entropy, and this is basically a log maximum likelihood inspired loss functions. And for the training, let's first say the task 1, we prepared the training examples using the conventional Monte Carlo approach. We only use such 2 ground canonical ensembles for the training. That's 10,000 configurations with chemical potential equals 1.05 and lambda equals 1.1. We label them as y equals 0.1. And 10,000 configurations with chemical potential equals 0.85 and lambda equals 0.5. We label them as y equals 1,0. Here, our target is try to differentiate configurations according to the lambda values. So we use this structure to train our neural network, try to differentiate the different configurations according to their lambda values. And in the test, we will fit in some unseen configurations, some different configurations from the training set and with different chemical potentials, but one with lambda equals 1.0, one with lambda equals 0.5, to see if the network can identify these 2 cases for the configurations. So the results is perfect. We can get around 99.8% accuracy. And we need to note that for the training, we only used 2 ensembles of configurations, and the test is performed on different chemical potentials values, but with the same 2 lambda values. So this is the first task. It's very good. Then for the second task, here is wrong, the second classification, we try to let the network to identify the phase of our configuration is in the condensation phase or in the non-condensation phase. We try to see if the network can identify the phase transition point. Here is 0.94. So for the training set, we used only 2 ensembles of configurations. One is at mu equals 0.91, chemical potential equals 0.91. It's here. It's well below the transition point. And one with chemical potential equals 1.05, which is here in this region. So it's well above the transition point. And we label the 0.91 configurations to be y equals 0.1 and label the other to be y equals 1.0. And once we trained the network, when we want to test, for the testing set, we prepared different ensembles of configurations at different chemical potential values. So basically, we will apply the network on regions here to see what the output would be. So because we applied softmax activation functions in the final output layers, so basically it's a S-shaped functions for one node, and we can interpret it the values of one node to be the probability of the function to decide the input is in phase 1 or phase 2. Let's say we use phase 1 to denote the phase below the transition point. It's a non-condensation phase, and phase 2 to be the phase above the transition point. It's the condensation phase. And the result is shown here. So here in this plot, I show the final output. We can call it a condensation probability from the neural network. And x-axis is the chemical potential values. So we apply the well-trained neural network on different ensembles of configurations with different chemical potential values. And each point is representing one specific configuration. So we have, for each chemical potential value, we have many points. So basically, we see such a collection of different points. Each point is one configuration. And we can see around here, there is some blurred phase structure information being decoded by the neural network. And to say if the network already has learned information about the system's physics knowledge, we can plot this condensation probability as a function of the number density. Because we know the number density for each configuration, we see here there is a jump. That means for a positive number density, the condensation probability would be non-zero. And here we also plotted the condensation probability as a function of the phi square value, the squared field. So it's also, once the phi square is above some value, the condensation probability would be non-zero. This coincides very well with the plot here. Here is from the conventional analysis on the configurations. This is the chemical potential. The green points are the number densities. We see once the number density, this is the average value, ensemble average, once it's non-zero, we can denote this point and the transition point. And once the phi square value is above, it's larger than 0.25, then we will meet the transition point. So it coincides very well with the result here. Once it's non-zero, then the condensation probability is also non-zero. Once the phi square value is above 0.25, not 0.25, 0.27, some number, then the condensation probability is non-zero. That means the neural network really gets some information about these correlations, about the correlation with the number density and the squared field value with the phase structure. And we further tried a much more deeper network structure. We just add one more convolutional layer to see what's the performance, and it do give us a better performance. We say that compared to the 2 CNN layers, the 3 CNN layers network structure can have a much more powerful, much more better expressive to learn from the configurations. It's much more distinct, the correlation it's learned. And here, we propose to use this average condensation probability to be some sort of order parameters here. So we plotted here this average condensation probability as a function of the chemical potential. We see here the non-zero value of this averaged condensation probability will indicate us the transition points very well. And from physics, we know to calculate this number density, we just need to accumulate the values of the KT variable. This might be very easy for the network. But from a conventional approach, we do not know the correlation between the phase structure with other variables. I mean, without the KT, physically, we don't know how to get the phase structure information from from only the LT, LX variables. So now we want to try if we discard the KT information, is the neural network still capable of detecting the phase structure information? And the answer is yes. So first, we tried only use the L variable. Sorry, here, this needs to be here, and this L is here, yes. So beyond a conventional knowledge indicating hidden structures in the L variables, and it's not only using the KT variables. So we say when we only use the LX, the network still can give us a very good indicator for the phase transition point. And for others, here shows 4 different cases. The green points are using the whole representation for your field configurations, use KX, KL, and LX, LT. And if we use only the KX or L variables, we can get similar results. Okay, now I want to show you the results on the regression task that we want to use neural network to learn the physical observables. And for this, we need to change the loss function to be the mean squared errors. And for the training set, still, we only use these 2 ensembles of configurations. So here is the result. And for the testing, we want to see the generalization ability. So we applied the trained network on unseeing domain of the number density of phase squares. So here shows the regression for particle densities. For the training, we only used these 2 parts. And for the test, it's here. And the formula is here. So the y-axis is the true value from the physics formula, and the x-axis is the network predictions. So we say it's doing a rather good job. And for the phase square value regression results is shown here. And for this, we need to note that the correlation between the configuration with this phase square value is a highly nonlinear relationship. The formula is shown here. There's integration. There's also some summations on different sides. And for the training, we only used this part and this part. But for the testing, it's still doing a very good job. That means we can use such neural network to do the nonlinear interpolation, and we can even generalize it to the whole target space even with limited training set. Okay, so I will not say this part because time is running, right? Do we still have time?
1 minute.
1 minute? Okay, so I just want to say that we also applied the generative adversarial network, try to generate new configurations. This can help us avoiding the Monte Carlo approach. And GAN is basically consisting of 2 networks. One is the generator, one is discriminator. So the generator will map some random noise from a prior distribution into hopefully the target space. So here our target space is a configuration space. So it's a 200 by 10, a very high dimensional space. So we want to generate the configurations just from some prior distributions. And there's also one discriminator network. This is to classify the input is a real training data or it's a generated fixed data. And we train these 2 networks alternatively, so they will beat against each other. And in the end, we will get a Nash equilibrium. And there, the generator can do a very good job, and the discriminator cannot distinguish these 2 cases. That means we already have a very good generator. And here shows the results. We can generate the configurations and to say if the generated configuration is physical enough. So we try to say if this vanishing divergence conditions can be satisfied, we see the value is decreasing, and here it's around 3% accuracy. So that means the GAN indeed has learned the structure of your configurations. It can generate new configurations. And also, we trained a conditional GAN. We use the number density to condition our GAN. We try to generate different number densities configurations. And this is very useful in canonical ensemble generation tasks. And here shows you the results. For the training, we only used these 4 points configurations. We have the labels for each configuration. We know the number densities. So we use this as the training examples. And when we test, we want to generate new configurations. We can specify the condition of the n to be different values. We can get different configurations, and it has rather well results here. And so here are the results. Thank you very much.
So as a physicist, so if you say the quantity, you didn't use K, am I right, in one of the plots, but still the other...
Which?
So you didn't use K in one of the plots, but you used L.
Yes.
And you said it still works. So what did you learn as a physicist from this? What is it in those configurations that
means
enough?
There is correlation between the number density with the L variables, but we don't know the formula. We don't know the physics, how to get this. But the network has learned.
So you cannot derive this, actually?
We want to, but still we didn't get to that point.
Thanks.
Welcome.
Okay, so let's thank the speaker again.